All right, in this video, we're still on chapter section 1.5. So now we're going to go through a bit of some examples in terms of our exponential functions. So reminder, exponential functions can be written as some p naught a to the t. So let's take this first example. The amount of adrenaline in the body can change rapidly. Suppose the initial amount is 15 milligrams. Find a formula for A, the amount in milligrams, at time t, minutes later, if A is, and we have these four different situations going on. Now, there's some differences in the wording between A and B and C and D. So A says increasing by 0.4 milligrams per minute, and specifically the word per here is going to be our big tip off. This is actually not exponential. This is actually linear. If you ever see the word per, it's most likely going to be linear. By most likely, I say about approximately 98% of the time. So since we have per here, this is actually representing a linear function. So we need some p equals m. Well, actually, let's use the variables that we were given. We're given an amount in terms of t. So a equals mt plus b. So we need the slope and we need the y-intercept. Well, remember that the y-intercept, you can also think about it in many contexts as the starting point, because usually, especially in this context, since t is time, we can't have negative time. So we're starting at time equals 0, so we're starting at the y-intercept. So since we're told that the initial value is 15 milligrams, that's going to tell us that our B is 15. And now this situation, this increasing by 0.4 milligrams per minute is what's telling us our slope. So since we're increasing by 0.4, that means that our slope is going to be 0.4. So the equation we're looking for is 0.4t plus 15. Now in part B, we still have a per kind of showing up, so we still know that it's got to be linear, but now we're decreasing by 0.4 milligrams per minute. So that's not going to change the initial amount at all. Our B value is still going to be 15, but what that is going to change is that's going to change the slope. It's going to make the slope negative. So here our equation would be negative 0.4t plus 15. Now in part C and D, we essentially have the difference is that it does have the word per, but there's a percent symbol and the percent wins out. So if you ever see a percent, whether or not it includes the word per, if you have a percent, this is going to be exponential. So it's kind of like the percent wins out over the per. So it's kind of look for the percent first. And if you don't see a percent, but it does say per something, then it should be linear. So we're increasing by 3% per minute. So we need some A equals A naught, I should say capital A naught, little a to the t. So it's unfortunate there's so many A's floating around there. But so we're told 3% per minute. So 3% is 0.03 as a decimal, okay? Now this is the rate at which we're increasing by, and the rate, if you go back to our definitions in the last video, the rate is an R value. So this means our R value is going to be 0.3. So then we have to find the little a value. Well, that's equal to 1 plus R. So we take this rate that we're increasing by and we add 1 to it. That's going to make our A value 1.03. And then A naught, capital A naught, well, that's our initial condition. So that's the initial value. That's still 15. So we still have 15 as our initial condition. So our exponential equation here is 15, 1.03 to the t. And then in part D, the only thing that changes is we're still at 3%. So we're still in an exponential situation, but now we're decreasing. So since we're decreasing, that changes the R value to negative. The A value is still found in the same way though. So we have 1 minus 0.03. So in this case, our A value is going to be 0.97. So you have to not only change the percent over to a decimal, but also take into consideration whether it's positive or negative based off of the context of the problem. So now we have this equation would therefore be 15 0.97 to the t, since our a naught, the initial condition, didn't change again. All right, moving down to problem 1. By the 1990s, wolves in Wyoming had been wiped out by hunters and put on an endangered species list. In 1995, wolves were introduced to Wyoming from Canada. Starting with 14 wolves in 1995, their number increased to 207 wolves in 2012. Assuming the Wyoming wolf population is growing exponentially, so we want an exponential function, find the function that represents the population t years after 1995. What is the annual percent growth rate? So there's a lot happening here. So the first thing we're asked to do is to find the equation of the exponential function. And just like with linear functions, we can find this as long as we're given 2 points. So the first thing I want to do is come off to the side and use this piece over here to write down the process for finding the equation for an exponential function given 2 points. And I'm kind of going to go back and forth as I write this step. We're going to then come over to the side and do it for this problem. So the first thing we want is we want to put both points in the form p equals p naught a to the t. And I'm going to suggest, because I know the next step that's going to happen, I'm going to suggest that you put the larger t value first. So you put whichever is the larger t value in an equation first. So let's go ahead and do that here. Well, the first thing I need is I actually need the 2 points that I'm working with. So the first thing I want to recognize is that we're asked to do t in years since 1995. So I have 14 wolves in 1995, and I have 207 wolves in 2012. So t is going to be essentially be our quote-unquote x value. So these 2 points are going to become 0, 14, because 1995 is 0 years since 1995. And then 17, 2007. Sorry, 207. 17, 207. Because 2012 is 17 years after 1995. So we have our 2 points, and now I have to put it into the correct format. So again, I'm suggesting we put the larger t value first, so that would be the 17 point. So we have 207. I don't know what p naught is, and I know that t is 17. And then we have 14 equals p naught a to the 0. Now, I did technically say something incorrect. We do know what p naught is here. We could figure it out. But once again, as always, I'm going to go the long way first, because you don't always know what p naught is. So sometimes you're going to have to find it in this way. So we're going to do it out completely, even though we could kind of shortcut because we know what p naught is already. But the full process is, once you have them written like that, you're going to divide the 2 equations. And this is why I suggest putting the larger t value one written first, because then we're going to divide the 2. And the algebra is going to come out much nicer if the one with the larger t value is on top. So we essentially have 207 divided by 14. I'm just going to keep it as a decimal. Now, the reason we do it like this is because these p naughts cancel out. So since we had 2 unknowns in both of these equations, we didn't know p naught and we didn't know a, being able to divide them like this gets rid of one of the unknowns. And then we have a to the 17th divided by a to the 0. If you forget, if you ever have something with the same base to 2 different powers and you're dividing those 2 things, you're going to subtract their exponents. So 17 minus 0 is 17. And so then if we take the 17th root of both sides, which again for your calculator might be easier to type in as the 1 over 17th power, that's going to give us our a value. So a here is going to be approximately 1.172. And so I guess I got a little ahead of myself because step 3 was solve for A, which we just did. So we just solved for A. I'm going to erase this reminder so that I have more space. So we solved for A, so awesome. So now we can use this A value to solve for P naught. Again, in this specific example, we could have shortcut that. We know that P naught's going to be 14 because that's the value when T equals 0. But let's just go about finding it anyway. So how would we find P naught based on this A? What you're going to do is you're going to take whichever one of these two equations makes you happier, and you're going to plug in A to it. So let's say we take the one with the 17 because it's the more complicated one. So we don't know what P naught is, and we know now that A is 1.172. If we solve this for P naught, we have 207 equals P naught times 14.8515. Divide both sides by the 14-ish value, and you're going to get that P naught is approximately 13.938. And you might be saying now, well, hold on, you just said that P naught was 14. Yes, if you don't, so we know that it's 14, so I'm actually going to use 14 for the actual equation. But because we have to round so many times, so I had to round here when I took the 17th root of 207 over 14. And because of this rounding, that's going to make this not exactly 14. And that's okay. This is still going to get us a decent approximation of this function. Excuse me. So since we know P naught is 14, it will use 14. But again, sometimes you don't know P naught from the information you're given, so you have to use this process, so I want you to see it. So that means that then, step 5, you can write the final equation. So we have P equals our P naught value, which is 14. A value is 1.172 to the T. Technically, we aren't done here because we are also asked what is the annual percent growth rate. The word rate should tip you off that we're looking for the R value. So whenever you see the word rate, that's asking for the R value. So we want R. Well, we know that A is 1 plus R, and we know that A is 1.172. Subtract 1 from both sides, you get that R is equal to 0.172. And since this is usually written as a percent as well, let's also switch it over to 17.2%. If it doesn't specify one over the other, decimal versus percent, whichever one you prefer, you can leave it as. All right, so we've got one more here in 1.5. So suppose Q equals f of t is an exponential function of t, with f of 20 being equal to 88.2 and f of 23 being 91.4. So essentially, this is kind of walking us through finding that equation again. So the first thing we want to do is find the base. So we want to find A. Remember, base means A, rate means R. So we want to find the base. So this is when we essentially need to write those two equations and divide them. So I have the larger t value is 23, so I'm going to write that one out first. So I have 91.4. Don't know what P naught is, and we actually don't know what P naught is here. Don't know what A is. T was 23. And in the other piece, we had 88.2 equals P naught A to the 20th. We're going to divide those two equations. Again, the point of that is that this P naught's going to cancel out. We're going to get 1.0363 is equal to A cubed, because we do, this comes from 23 minus 20. You take those two exponents and subtract them. And then to find A, I have to take the cube root of that 1.0363, which is going to get us approximately 1.012. And again, there's lots of rounding going on here. So there's lots of places for people to get slightly different answers depending on how much you round. I always suggest rounding to 3 decimal places. So we found A, we found the base, we're done part A. Then we want to find the percent growth rate. So the word rate should tip you off to the fact that we want R. So if A is 1.012, and A is also equal to 1 plus R, then we have that R is equal to A minus 1 if you just subtract 1 for both sides of this equation. So R is equal to 1.012 minus 1, so 0.012 or 1.2%. And then the last thing we're asked to do is evaluate f of 25. Now to do this, we first need Q naught. Now, why am I saying Q naught and not P naught? Because I should have been using Q's this entire time. So these two up here should have technically been Q naught. Why Q naught and not P naught? Well, that's because this original equation was given as Q equals f of t, so I should have been using Q's. So that was my bad. So we're going to call it Q naught. So we need to find Q naught first. Well, that is when we take whichever one of these two equations makes us happier. We use the A value that we found to solve for P naught. I'm going to use the one that involves the 20th power. So I would personally pick 88.2 equals Q naught 1.012 to the 20th. So then we have 88.2 equals whatever Q naught is times 1.269. And again, I'm rounding here as well, so some of you might get slightly different answers depending on how many decimal points you take. If you want the best answer possible, you want to round as little as possible. So this is going to get us approximately 69.5. So we can use that Q naught now to actually find the full equation. So the full equation would therefore be Q equals 69.5, 1.012 to the t. And now that I know the full equation, I can do what I was actually asked to do and evaluate f of 25. So I want to plug in 25 to this equation. So 69.5 times 1.012 to the 25th. Which will give you 93.648 approximately. So that is our value of f of 25. So those are our examples of exponential functions and how we're going to be able to use them. In 1.7, when we get around to it, we'll be doing some more with exponential functions. But for now, we're done 1.5. This has concluded 1.5 notes and the lecture for today. Let me know if you have any questions.